These are the questions we're picking for soil and water measurements. I'm doing changes in dissolved oxygen over time. In our experiment, dissolved oxygen was the most volatile variable in our measured results by far. After adding the fish, we saw a significant drop in dissolved oxygen levels due to the use of oxygen in cellular respiration. Dissolved oxygen also decreased when the fish was added because its waste goes through the aerobic decomposition. The presence of the Elodio plant allowed excess carbon dioxide to be converted into oxygen through photosynthesis, which is why we saw the DO levels increase again. Fluctuation can be explained by the cycles of waste being produced and broken down by bacteria, which consumes oxygen and releases carbon dioxide through cellular respiration. And the Elodia's photosynthesis converted the carbon dioxide produced by fish and bacteria to oxygen. Dissolved oxygen levels can also be influenced by temperature, as cooler water can hold more oxygen than warmer water. But I don't think this played much of a role in the experiment, as water temperature remained relatively constant over the course of the experiment.
This is the question that we picked for the changes in water pH over time. I'm going to be talking about the graph on the right. Water pH is determined by a very wide range of factors, but the strongest influence was the original water source, which is the tap water from Huntington Beach, which was dechlorinated. That sets the pH anywhere from a range of 7.5 to 8, which generally matched our pH. However, due to the Elodia's strong photosynthesis that increased the dissolved oxygen whilst consuming carbon dioxide, our pH had a bit more variation depending on the stage of photosynthesis the Elodia was in. Decomposition also played a role in the pH. However, we were careful about removing any decomposing matter, so it didn't have too much effect on the experiment. Even seemingly small modifications in pH can be significant because it's based on logarithmic graphs to the powers of 10.
All right, so now we're moving on to the questions that we'll pick for adjustments, observations, error, and design. So, what were the most significant observations? I'm answering that question. And I'm using these two graphs over here of corn growth and moonflower growth. Some of our most significant observations were in the visual growth of our plants, including our Elodia, which is not displayed here, as well as the growth of the plant. To accommodate, I made a mistake. I meant corn and moonflower in my speaking. You could see that displayed on these graphs. So, as I was saying, our most significant observations were in the visual growth of our plants, as well as the growth of the plant roots to accommodate the increasing size. We were interested in the ability of the corn and moonflower roots' ability to penetrate not only into the filter chamber, but into the water chamber at the bottom. The squash and alfalfa that were unable to spread their roots as far died, and were likely outcompeted by these more aggressive plants in the Ecocolumn, which were better suited for the conditions in the Ecocolumn. We also previously discussed the changes in pH and dissolved oxygen in the water, which were interesting to observe over time since we did not necessarily have obvious explanations for these changes, as our Elodia had not died, and some of the fluctuations occurred before the inclusion of the fish.
The other question we wanted to discuss is how each of the chambers in the ecocolumn affected the other chambers using the graph on the left. The terrestrial chamber had a large impact on the aquatic chamber, mainly because of the roots of the moonflower and possibly of the corn grew into the chamber and drew water from it. In turn, the aquatic chamber impacted the terrestrial chamber by providing it with nutrients both with the water taken directly from it and by adding nutrients to the soil with the usage of its water to water the plants in the terrestrial chamber. The live fish also excreted waste that was converted into usable phosphates, which were given to the plants through watering from the aquatic chamber. The introduction of detritivores into the terrestrial ecocolumn helped to aerate the soil and create an ease of water flow, which benefited soil productivity.
These were the scientific questions that we wanted to ask ourselves, but were unable to answer quite yet. In our experience, we were curious as to why the squash and alfalfa were the first to grow and dominate the environment, but were quickly outcompeted by the late bloomers, the corn and the moonflower. We also wondered how, despite the same soil and resources, how our crops became more productive and successful than the ecocolumns for the other groups.
In the experiment, why did the fertility of the soil remain zero despite the presence of leaf litter and detritivore and the usage of the same soil as other ecocolumns who had higher fertility levels?
We were also asking, why did our nitrite and nitrate levels remain low or zero despite the presence of fish waste and Elodia to convert the ammonia into nitrogen derivatives?
And finally, for our fifth question, why were some detritivores more successful than others? Why did our mealworms die when they had a higher population, but our roly-polies were successful enough to reproduce, despite the same limiting factors and a smaller initial population? That was our project. Thank you very much for listening to our Ecocolumn final video submission.